Okay. Screen sharing. Okay. So when you mean to make such a decision, we're basically, and I'm just quickly showing the slides again from last time. So you standardize the differences from, we remember all this concept about set scores and the population, how we're stratifying, how we're standardizing it according to the standard deviations. Now we're calculating basically a set statistics for group comparisons. So again, we're looking right now not at individuals in the population. We're looking at a distribution of means from hypothetically drawn samples to compare based on our one sample that we have, that we're comparing to the population mean. We're now thinking of a hypothetical number of samples that we have drawn that provides each of them one mean. And this distributes around that mean from our sample with a certain distribution. And we're comparing based on this distribution of the sample means. We're comparing and investigating or analyzing the probability of that mean of your sample being significantly different than the population mean, thereby rejecting the null hypothesis that your sample mean and your population mean are identical. That is the null hypothesis. So you do that by calculating this difference, a difference between, it's not a good slide, calculating a difference between the sample mean and the population mean. And you standardize this sample mean and population mean, this difference, by your standard error of the mean. And the standard error of the mean conceptually is the distribution of these hypothetically drawn samples from your population that build a distribution of means around that mean of your sample. And if your set statistics exceeds a critical value that corresponds with a 5% probability, within this 5% probability, you would still need to make the determination that your sample mean comes from the same distribution and is the same as the population mean. If you have a set statistic that exceeds the corresponding p-value of 5%, then you will reject your null hypothesis and you accept the alternative hypothesis of the sample mean being different from your population mean. So now this unfortunately tells you only half of the story, because just because you have a significant difference, yes.
But I thought if the p-value is less than 0.05, then you reject the number.
Correct.
Oh, okay.
That's what I said. No?
Okay.
Did I misspoke?
I don't know, but
I may have misspoken. No? Did I not? Okay, let's watch the recording then later. So no, definitely, if it's smaller than 5%, you're rejecting the null hypothesis. If I misspoke, my apologies. So now that only tells you half of the truth, because it's not only about the significant difference, because that's only half what really counts. And the example that Neumann and Heinzen are using now in confidence intervals is an interesting one. So this is an analysis, which basically, so there are some older claims, older studies, so that's fairly old already, that's like 30 years old. But essentially, insights and analyses like that kind of were represented the advent of looking more into what is called, and Neumann and Heinzen will call it new statistics. For the reason, because new statistics take into account these confidence intervals, these variabilities, which we will discuss today. They take into account the distribution and do not focus solely on the rejection of a null hypothesis. So older work than this has claimed that there are differences in mathematical knowledge, mathematical understanding between men and women, which is a debatable topic essentially, and yeah, I don't know, there are biological differences which one cannot reject, and there are psychological assessments, but are they in essence really as important as some of the previous studies claimed? So first of all, so this meta-analysis, and we will talk later what a meta-analysis is, basically concluded that the gender differences, it's actually sex differences nowadays, in mathematical reasoning are very small. And they focus on the extreme tails of the distribution. And the gender difference depended really on the tasks. So females were better with computation, men were better with problem solving, which whatever that means, there's I don't know what the associations are, I'm not a psychologist, but essentially what this means to illustrate is if you take the ends, the extreme ends of, you're basically looking at more or less identical group. So you compare here males versus females, with females being slightly up on the higher end, but basically they kind of cover the same thing. The only thing that's really different in the concept of a normal distribution are these extreme outliers. And this is where just focusing on hypothesis testing is misleading, because you will see hypothetically, if you have a large enough distribution, you will find significant differences between the dashed line and the solid line. And you may conclude that if you study 100,000 students all over the US, and you separate them as per gender, and you make these assessments between the two genders, and you find a significant difference, you cannot conclude there's like one gender or one biological sex is better than the other in mathematics, because overlap, they're quite comparable. The only difference you see are these extreme outliers. And that needs to be taken into account whenever you look at statistics. And I made this point that it really requires focus and understanding of the parameter per se. So if you compare blood pressure between two groups, you need to understand how meaningful is the difference between two different means in two groups, whether it's a hypertensive, antihypertensive group, or the group with no medication. So you need to understand how that distributes, and you need to understand all ins and outs of that variable, and you also need to understand how meaningful is a difference. If you see a difference in, let's go back to our homework example, and assembling a kitchen unit, and you see a difference by 5 seconds, and you study 1,000 people in one group and 1,000 people in another group, or one age group versus another age group, and they're 5 seconds apart, that means nothing, right? It's not meaningful as a difference, although it still can be significant. And that's where the tricky part of interpretation of statistical results is. Sometimes you see, sometimes you see differences, but they are essentially not meaningful. Is that too dark? No? Okay. So this is important to keep in mind, and particularly this overlap is particularly important to keep in mind, because the majority of people are still kind of coming within the same, or still distributing in the same range of STAT score. So also important, and this is which comes down to the conversation, whether there are essentially, you remember p-hacking, and where you basically use subset and you find then differences. So differences were dependent on the task. So you gotta make this again hypothesis driven, whether you test males versus females, because otherwise you're just going down the pathway of subsetting. So that's one of these examples where p-hacking, for example, could be conducted, could be assumed. But it's not really the case, because this was a task-driven kind of comparison. So if you do different tasks and somebody is better at one task but not as good as the other task, this is a fair comparison. It's a comparison by design. But basically, this is what you need to keep in mind. Irrespective of significance, there may still be substantial overlap between the population that you're comparing. But it gives us now a little bit of a taste of what Norton and Heinzen keep on calling the new statistics. So new statistics are moving into the mainstream. So hypothesis testing may encourage researchers to massage data until they approach the criterion of less than 0.05. And this comes back to Norton and Heinzen's graph with 1.996, and there's a mode, a high occurrence of research publication that showed a SAT score of 1.96 that corresponds with a p-value of 5%. So it is not impossible, and p-hacking also goes in that direction. You subset until you finally see a significant result and you see something that the journal would possibly accept for publication. But now the new statistics, and I haven't heard the term new statistics before I started teaching this book, but basically the new statistics involve effect sizes, confidence intervals, and meta-analysis. I've heard those three terms, but not unlabeled under the umbrella term of new statistics.
Is that not in old statistics? Like that's the new.
Yeah, old statistics are the traditional statistics. So that's what they mean to express with that. The old classic statistics, they would do mean, a little bit of a variability, and then basically just do a p-test, a set test, and provide a p-value.
You wouldn't do as much inferentials.
But they draw inferences just out on the p-value, but they don't pay attention to the variability and the effect sizes. And that is Norton and Heinzen's point. Good. This being said, we will learn about these new statistics, and please remember the term because it will be coming like that in your quizzes. So we will talk about effect sizes, confidence intervals, and meta-analysis today. Firstly, let's go to confidence intervals. So when you have a confidence interval and you have a mean basically is a point estimate. So you have a sample and you get a mean. This mean, now leave hypothesis testing apart, but you assume that I randomly sampled from the population and my mean is the estimate of the population mean. I have no reason not to believe that this is not consistent with my population mean. It is not true in most cases because random sampling is difficult, right? But what I do have, yes, Daniela?
I thought we said maybe last class or class before that even if you take from a random sample, you take a mean that it is representative.
Exactly. And well, you cannot a priori assume it's representative. It's an assumption of a point estimate. That's you're sampling, and from that point on, your mean is your point estimate of the population mean. And then you need to compare it. Random sampling is practically impossible, very difficult. And thereby, it's hard to believe that it will actually be identical to the population mean, as it should be in a perfect world. But in a perfect world, I would do a random sample. I would just like pick out 1,000 people from the telephone book and basically sample them. And they will all participate in my study. But this is just not happening, but it's a point estimate. And that's the point, right? It's like they mean to estimate the population mean by collecting a sample, which is meant to be randomly sampled and coming randomly from the overall population distribution. So that's a point estimate. So a point estimate obviously is unlikely to be point on, and although it's our hypothesis and our null hypothesis in hypothesis testing, what has a higher chance of actually representing the population mean is a so-called interval estimate. So you have a sample statistic, which is a mean of your sample. You have a variability of your sample. You have a standard deviation from your sample moving forward. But you have a standard error of the mean, because you know that mean, if I draw repeatedly these samples and I get a repeated number of these means, they will distribute around my sample mean, following that relationship was the standard deviation, a little lower because it's divided by the square root of the sample size of my sample. And that's why my standard error is going to be smaller, but it will distribute following a normal distribution. And you remember those graphs, right? Wide for the population and very skinny for the distribution of the sample means. Yes.
Is it good if like, is it the mean you have more accurate results if the mean, if like if it's skinny around the mean, meaning that
Yeah.
it's closer to,
It's closer to reality.
and that means that your sample was high, like more likely that it was truly randomly selected.
That would be more the distance to the actual population mean, if the population mean is known. What it would mean is that there's less variability, because if you randomly sample, your mean will be more accurately reflecting the population mean. If you get an equally random sample, it will again quite narrow and quite accurately reflect the population mean. So there will be less variability for the reasons of sampling. What's the main drive for this narrow skinny distribution curve will be high sample size. Because the more people you sample, the more participants you sample, the more accurately it will move towards the population mean.
How does that work?
Sampling?
No, like why if you have higher sample, would the sample be more likely to represent the mean of the population?
Correct, because it's more from the same distribution. You randomly sample, you randomly sample, you reduce, so outliers, your mean is dependent on outliers. But if you have a majority of sample participants basically drawn from the bulk of the normal distribution curve, which likely you will have, and it's really somewhat random there, that little outlier doesn't make a difference anymore. If there's one outlier, 10 outliers, doesn't matter if you have 100,000 people, right? So it's arithmetically. Yes?
I'm confused by this. You said when you take a bunch of the samples, when you take a bunch of the sample means, and then you graph them back, it will be a normal distribution if you graph all means.
No, if you take one mean, you have one sample, right? You have one sample, you get 1 point estimate of a mean. You're saying at this point, okay, so I randomly drew that sample. I think that my mean is representing or is identically to the population mean. So now that may be true or may not be true. So there's a certain kind of variability which you are expecting with each sample that you draw, right? Every mean, if you draw 100 means, you expect a certain variability in the mean estimate, in this point estimate. That is the standard error of the mean. Standard error of the mean. And that standard error of the mean is dependent on the standard deviation of the population, because the more variability you have in the population, the more closely this will be reflected in the standard error of the mean as well, because you're more likely to get outliers. So that's how this relates to each other. But the higher the sample size, the more accurately it will relate and will reflect that population mean, and the less variability you will have, because you're more likely to get accurate results. Okay, good. So interval estimate. So now you have, basically you have a mean, and you know now that there's a certain variability around your mean, which is following the distribution of the sample means with the standard error of the mean. So now there's a certain probability with which you will have that population mean actually captured within your interval. And that probability is reflected by what is called the confidence interval. So in the simplest approach, and I'm going to these slides here. So this is showing now exactly this relationship. Central limit theorem, mean of the population sampling distribution is identically. Standard deviation of the population related to standard deviation of the distribution of the sample means. We've seen that formula. And the sample size will basically get it closer to the mean. So now we want to have something else. Now we want the point estimate to be amended and supplemented with an interval estimate. And now, okay. And now you can also, reflect that probability of containing your population mean by the distribution of your sample means. So if you do hypothesis testing, remember we're calculating the difference, we're standardizing the differences, and we're saying, okay, we're rejecting this at an alpha level of 5%. So with more than, so with less than 5% probability, we essentially were looking at a sample that is different from the distribution, from the population distribution. So likely it's significantly different. So now we can quantify the confidence with which we contain our population mean within the variability of our sample mean, to build two intervals surrounding that sample mean. And this is here called a 95% confidence interval, which is the inverted of the 5% alpha. It can be a 99% confidence interval. Can be a 90% confidence interval, also quite commonly found, or it can essentially be a probability of any confidence you aspire to do. The idea here is to essentially, you look at the standard error of the mean, of the distribution of the sample means, and you're standardizing that distribution. And you say, okay, so this is the interval within which I am 95% confident that I contain the population mean. If my population mean, then in hypothesis testing, because you can also use it for hypothesis testing, if my population mean is outside of this interval, I'm less than 5% certain that this is within it, and I likely look at a significant difference. So this is where this intertwines, right? So the interpretation of that is essentially, okay, we're calculating now. Let me show you that formula again. So I have a mean, I have a sample mean, and I add 1.96, which is 2.5% to the left tail, 2.5% to the right tail. I subtract and I add 1.96 multiplied by the STAT score. So subtracting, I get the left tail, the 2.5%, and I add it, I get the right tail. So I get that interval of my distribution of the sample means that is basically demarking the extremes. So the 2.5% to the left and the 2.5% to the right. And that adds up to 5%, which is essentially 1, like the entire population, or 100%, minus the 5%. I know it's a little rough, but you will follow me. Let's go back to hypothesis testing. Yes, sir. We're gonna go over this. No worries. Let's go back to the slide. As a recap, this is hypothesis testing. 1.96 demarcates this extreme, plus 1.96, minus 1.96 demarcates the lower 2.5%.
Where do we get these numbers?
1.96 from the STAT score table. STAT score table 1.96 associates with.
Always comes back to this table.
It always comes back to the table. Yeah, because the table is representing the percentages calculated by the function. You remember I showed you this function of the normal distribution curve, right? So this function basically builds out this curve. And now we're moved away from standardizing population. Now we're standardizing probabilities. And we have here probabilities of having the mean inside, right? The population mean. And
0.9750.
Yes, 0.9750. This is 1 minus 0.9750 is 2.5%. And if you go for minus 1.96, it will be 2.5%. If you go to 2.58, it will be 99. It will be 0.05. So essentially, you are characterizing now these extremes.
0.9951.
Exactly. So you're characterizing these extremes, and that's your interval within which you're 95% confident your population mean needs to be in. If it's not, your population mean is significantly different at a alpha level of 5%.
So does that mean your sample mean is not accurate in representing the mean of the population?
Exactly.
If it doesn't fall within the confidence interval.
Exactly. If the population mean is not within that interval of your sample, then you have sampled a different population. Yes.
What was the part about the 5%?
The what?
The part about the 5%.
So we have a cutoff, a so-called alpha level, below which we are basically defining a type 1 error. You remember type 1 error and type 2 error. Type 1 error, we're rejecting something which we shouldn't have rejected. Yeah, so that's the so-called alpha, because we're defining a maximum of 5% type 1 error that we're willing to accept. Or we only accept 1%, then we're looking at 1% alpha.
Type 2?
No. That's the type 1 error exclusively. Type 2 error is different. Type 2 error is where we're not rejecting, although we should have rejected. And we're getting to that when we talk about power today. Actually, I gotta hurry. Yeah, yes.
I don't understand when we use the different, like what makes us use the different confidence intervals?
So that's a definition. Good question. In 95% of our research, you will be using 95% or 5% alpha level. In very large samples, because with higher sample sizes, larger sample sizes, you're more likely to find a significant result, although it's clinically not meaningful, you will choose a lower alpha because it's a smaller probability or risk of a type 1 error. So particularly with large samples, you really want to minimize the risk of a type 1 error. So, but what does this also mean? How do you interpret this? So let's look at this. And this is I like this graph. It's a little busy, but it's pretty amazing. Because what you're looking at, so I keep on talking about these repeated samples that you draw, and you build out this distribution of the sample means, right? I keep on talking about that, and this is the graphical depiction of exactly what I'm talking about. So we're having a mu, which is our population mean, the blue line. Bless you. Now we're having samples, and for each of these samples, so these are 100 samples. For each of these samples, a confidence interval was generated, which starts on the very left of that little line and ends at the very right of that little line. So that confidence interval for the first one contains the population mean. The second one also contains the population mean. Third one also contains the population mean. Fourth one is not containing the population mean and is significantly different from the population mean. What the 95% confidence interval expresses is a probability within which you're confident to capture the population mean. That means that out of 100 samples that you've drawn, 95 contain your population mean. If they don't, you're rejecting. So that's the graphical depiction of what we're essentially doing with hypothesis testing, and that's why I love this graph. Any questions to that? I know it looks more confusing, but I think you're slowly molding into it. It's conceptually hard, but it's really about coming back to the basic principles of probability. We have started standardizing the population distribution with the STAT score, and then moved away, and then we're building up a hypothetical distribution of hypothetical samples that were drawn, And we're using this conceptually to determine probabilities of a difference being significant or not. And that's kind of the continuation of the SAT process to go into employing this on that sample that you have at hand. So if you have, let's say you have, you're sampling 100 students from all the students in the US, and you determine SAT score of, what's a good SAT score? I don't know. Let's say it's 1400. Okay, 1400. You have a sample of 1,000 students. Let's get a good sample, and they have a mean of 1250, and the population mean is 1400. And you are now trying to figure out who are the people in the sample? Are they worse than the population, or are they from a different part of the distribution, or is this school not good? I don't know. You basically, you're looking at that sample mean, you're building that sample mean, and then you look at the size of the sample and you look at the variability that you know from the overall group, from all the US students. You take the standard deviation and you build this distribution of the sample means around your sample of 1,000 students that you have sampled from wherever. And you build a confidence interval around that mean, and you see that the confidence interval does not include your US population mean. You know that's a very distinct group of students, and they're not representative of the US population for whatever reason. And you're doing that by this hypothetical construct of the distribution of the sample means around your mean at hand. And you're building confidence intervals to reflect how much variability do I have to expect when I draw samples. All right. Any questions? I see skeptical looks, but no. Well, let's carry on for now. We have, but okay, how to calculate the mean? Yes. No, we're not doing that. But but this is now why we have 3 lessons. So we have on Wednesday we're gonna go through the material of the confidence interval and hypothesis testing again. Next week we have a lab day where we're gonna practice this in R and Excel. And on Wednesday, we're going to do a specific review class for the midterms. You're going to be fine. We're going to go through that, but bombard me with questions, please. Go through this, go through the lecture recordings, go through the material and ask your questions. Okay, so back to this. We have, okay, point estimates, interval estimates. So confidence is an interval that includes the mean expected for the sample statistic at a certain percentage of time at a certain probability. So if the same population is sampled repeatedly. So that was what I shown you. Right? Includes the range around the mean when the margin of error is added and subtracted. The margin of error is the numerical difference from the mean to get to this set score of 1.96. You will hear margin of error in political polls, surveys, in magazines, and in the news. The margin of error does the same thing. You have a political survey coming up, so now the midterms are up. You will hear political surveys, you will read political surveys. Whatever survey institute is going to call up 1,000 people, they get varying opinions, whom you're going to vote for. So you basically, what you get a certain margin of error. And this margin of error is basically determined based on the variability in the population and basically on the variability of your sample. And based on that sample, you will have a certain margin of error within which you are confident that people will be voting at the upcoming elections. This is where you most likely have heard margin of error. There are other examples, but it's not that mainstream. But in news, in political surveys, it's quite common thing to see those. So calculation. calculation of confidence interval. We talked about it already, right? So we have a lower and an upper bound. And there's 2 times lower. Where's that? That doesn't make any sense. Okay. Okay, so they insist on calculating this a little different, which I don't like. But basically, you take the negative set, multiply it by the standard error of the mean, and you add it to the sample because it's negative. I would do it the other way around. I would take the mean and subtract the negative sample. So you're going downwards, right? And the upper bound, which should be labeled here as upper bound, is adding it to the mean. So you get boundaries around the mean. Why is this lower? This is upper. Okay. So now how that is essentially conducted is super easy. We have had a couple of examples last time. Let's do that. We have here. I don't want to go too long into examples today because we have quite a bit to cover. So if you have here this example from last time, you remember, so we have an X bar of 150, we have a population mean of 160, and the standard deviation is 100. We want to calculate based on that. We want to calculate, so ST is 100, mean is 150, SEM, sample size is 300, that's the 300. So your standard error of the mean is the standard deviation divided by the square root of the sample size, right? So that's 5.77. So now if you want to do hypothesis testing, you calculate a set. A set is calculated as X minus the mean. The population mean is 160, so this set minus 160 divided by the standard error of the mean. So that's the set. So we know our set is at minus 1.73. That means that your mean is larger than your sample mean. If I want to calculate now, and now remember how this is being calculated, right? Because the only thing you're doing now, you're just rearranging this formula. So you have the standard error of the mean. You're multiplying your set of 1.96, which is 95%, with the standard error of the mean. And you're adding your mean. So what you're doing is, so 1.96, this is now the 95% confidence interval. So you do 1.96. So the mean we said is 150. So you want now first a lower bound, and then you want an upper bound. Lower limit, upper limit. Lower limit, upper limit is calculated now as 1.96 multiplied by the standard error of the mean plus your mean, which is 150. So that's the upper limit. So the lower limit is now your mean minus 1.96 multiplied by the standard error of the mean. That's 138.68. So now what do we see here? We have now an interval, which is basically surrounding a mean of 150. That's our mean. That's the center of the distribution. We have an upper limit, which is 161, and we have a lower limit of 139. As we know, our set was minus 1.73 is not less than minus 1.96, so it's not significant. So this p-value is greater than 5%. And this is also reflected here with the 95% confidence interval, which does not contain the population mean, which does contain the population mean of 160. So because it is captured within the confidence interval, we're not rejecting the null hypothesis. So this is where hypothesis testing and the confidence intervals are actually overlapping. You can basically utilize both. If you want to test yourself, you're willing to say on a quiz that this result is not significant, you can hypothetically test this by calculating the confidence intervals manually. It's basically like mapping out the normal distribution curve and doing it with the critical values of set, just like Nolan and Heinz suggested last time. You can also do this with the confidence interval, then it gives it a numerical value. It's just important that you know what your critical value of interest is. If you have 1.96, that's 95%. If you do 2.58, it's essentially further, it's 99%, but to have a higher confidence. Also, when you keep in mind, the wider you go out, the greater your probability that you will capture the population mean. Thereby, your confidence increases, and your type 1 error that you're rejecting something you shouldn't reject decreases. Any questions on these calculations? It's simple, right? It's not difficult. It's not. You're basically you're determining these critical thresholds, and you see where is my population mean in reference to that interval. If it's outside, it's significantly different from my population mean. That's what the confidence interval means. It helps you. It aids your decision.
Then it's not. If it's in like the green portion, then that means it's not
exactly
similar to the mean.
If it's in here, if it's in the main part, it's now you're accepting it. If it's in here, you're accepting it because it's not outside. It's not your set score is not greater numerically than your critical value. In that case of a negative set score, it would need to be lower, because the negative set score only means like that the mean was the population mean was larger than the so it's going in that direction, but it's the absolute
like
value.
0.05, that's not it. Like the p is less than 0.05.
That is the point. That is only the case at these two values. Everything outside is a p-value smaller than 5%. So this is the calculation, which is considerably simple and aids your decision making when it comes to hypothesis testing. So you're describing exactly that. These 2.5%, you're describing that. Yeah. So we just did that. So now we have a problem with sample size, right? We talked about this. So the larger the sample size, the smaller your standard error of the mean. The greater, the larger your set score. So the standard error of the mean is calculated by taking the standard deviation from the population, dividing it by the square root of the sample size. That will lower your standard error of the mean. If the standard error of the mean is smaller, it will result in a greater set because the denominator is smaller, right? Even in the presence of an equal numerator. So therefore, somebody very smart came up with the idea that we actually need to find some way to characterize differences in hypothesis testing unaffected by sample size. The way to do that is to calculate the so-called effect size. So you're standardizing now. Again, you're standardizing in the same fashion. So here with this formula, You're basically doing it by standardization of the standard error of the mean. We just talked about the standard error of the mean is affected by the sample size. The standard deviation is not. That's why it became a good idea to quantify the effect size. So what that means in principle, if you have essentially two equally distributed populations and you're comparing those, the overlapping part, it is essentially not helping your hypothesis, right? So your effect size will get larger if the differences get larger, or alternatively, when the variabilities get larger. So here you see there's like this faint line, you see it better on the slides. This is the same difference. So these are the only, so you have numerator and denominator. Denominator is basically the standard error of the mean when hypothesis testing. The numerator is the difference between the sample mean and the population mean, or like in this case, the two sample means. So in the presence of an equal difference, what matters here in regards to the denominator is the variability. So if you have less variability, larger sample sizes, you will get differences just for the sake of decreases in the variability. So these two slides are quite important to keep in mind, because you can essentially, you have, here's the numerator, the difference between the two means, and you have here the variability as the denominator of that estimation. So now logically,
So what's the definition of effect size?
effect size is where these two curves are not overlapping. So it's basically the strength of the difference.
And what
Yeah,
do
that's a
the
good
two
way.
curves represent?
The two curves are two different populations.
They're not samples of the same populations, they're completely separate.
It depends on the use case. For now, just two populations. Just keep it simple.
Why would they be, like, why are we comparing the two separate populations?
Well, you could compare two sample populations. It can be samples. You can compare Canadians versus Americans, Mexicans. So it's populations, right? It can be sample populations. It can be, the populations really depends on your definition to a large extent. You can compare, I don't know, New York versus Jersey City, and you can compare whatever population you define. But it's really what the main message here is. Only two things count: the numerator, the difference between both means, or the denominator, which is the variability. And therefore, you needed something that took the variability and the standard error of the mean problem, that this is affected by the sample size, out of the equation. Because only these two are basically operative. So the means are further apart or the variation changes. And therefore, statisticians have come up with D, the effect size. So Cohen's D is basically an assessment of the difference between the means. Instead of dividing it by the standard error of the mean, dividing it by the standard deviation. Because the standard deviation is not affected by the sample size. It is to some extent, but it's not really. And if you do that, you essentially, you get again a standardization, but this time the values are smaller. And these conventions, please also study these conventions, or at least know where to find them on the quiz. You basically, you have three different magnitudes. You have small, which is 0 to 0.2. You have medium from 0.21 to 0.5, and you have large from wrong, 0.2 to 0.5 is small. 0.5 to 0.8 is medium, and greater than 0.8 is large. And here on the side, you have a characterization of the overlap, because with a small effect size, you basically have 85% of your distribution curve overlapping. With medium, you have 67% overlapping, and with large, you have 53% overlapping. So lastly, so many minutes, but we're going to repeat on Wednesday. Lastly, we briefly talk about meta-analysis. We're not going to get to power today. I think meta-analysis is going to keep us busy. So a meta-analysis, if you do a randomized controlled trial and you get a significant difference on your trial, the NIH is happy because they supported you with their money and they're happy to see a good outcome in the study. You're going to be happy because you get good publication out and laid good ground for future publications. And then suddenly you have a second group from a different part of the country doing the same thing, finding different results. The most important thing to establish causality, and we talked about this, is replication. You replicate findings, right? And research bases on that. Never just one study. You always need a larger number of studies. So you are, for that purpose, you will find, and there's actually a very highly regarded group in the UK, the Cochrane group, that does nothing else but meta-analysis. They studied, they have a database for meta-analysis, every topic of potential interest. You see a characterization of all the published research. It's a fabulous, fabulous, fabulous database. So basically, a meta-analysis involves the calculation of a mean effect size from the individual effect size of more than one study. Okay, so if you have 10 different people studied the same research that you did, you have 10 different findings. So a little hard to say then what is better, right? You have 5 report effect in that direction, the other 5 report an effect in the other direction. So for that very reason, you are conducting meta-analysis. Meta-analysis looks like that. So we talked about the effect sizes, right? So we have effect size small, 0.5 to 0.5, 0.2 to 0.5, medium, 0.5 to 0.8, large, greater than 0.8. So now here you have basically in what is called a forest plot, because this basically shows a branch for each study. You see estimates of these effect sizes and the corresponding 95% confidence interval. So you see this depicted here on the side. I'm flagging this way of depicting data because that's how you will depict data moving forward. If you publish something in a scientific journal, you have here first your estimate, which can be a mean, which can be a coefficient in a regression analysis whatsoever. And you have then following parentheses, and ways how people depict that differ. But basically here in the brackets, you show the lower limit and the upper limit of your confidence interval.
That's like your margin of error.
That is the margin of error. That's the lower limit and the upper limit. What we calculated before for the weight of, what was it, milk cows or something. So you get now different estimates of effect size. Can be negative, can be positive. And then you build one overarching effect size for all. I spare you the details how that is being calculated because I've worked on a meta-analysis for the last 15 months with colleagues, and I'm not how should I say, I'm not the highest statistical reference, but the colleagues that have built this model, because there so much goes into this model and it's so difficult to build this complex model to actually get such an estimate based on so little data, right? You have variability, you have individual estimates, and you need to factor this all in to get this diamond estimate, this overall overarching estimate. So it's a wonderful tool, and it's basically something which should be done for all research topics. But it's a lot of work. And lastly, so since we have here a significant effect, as you can see, because it's larger than 0, so it has a significant effect. If you had another study that would show no effect. This would lower the effect. And if you include a large number of null studies that did not show a significant effect, this would at one point get your estimate to 0. If you do 1,000 studies then that all show no results, no effect, this would go and move towards 0. So now there's lastly, and that's the last topic for today for the last 2 minutes, there's a so-called file drawer analysis, which is a hypothetical estimate of how many null studies you would need to find in the literature to render your significant result from your meta-analysis a non-significant result. And that's basically, it's a simulation of how many studies are somewhere in a file drawer and have never been published and would hypothetically refute this significant difference that you're claiming for your meta-analysis. All right, thank you very much. Have a good evening. And I hope you understand now why I made 2 lectures out of confidence at the one, because that's quite heavy. You're welcome. Bye-bye.